Throughout the 1900s, physicists performed many experiments on light to see how it behaved. In some of these experiments, light behaved like a wave. For example, in the double slit experiment, shining a beam of light on a surface with two slits causes the beam of light to diffract around the slits and essentially split into two new waves that spread around from the slits. In this image, the lines represent the peaks of the wave. When the peaks of two waves interact with each other, they add up to create a larger wave with a larger amplitude. In other areas, the peaks and troughs of the wave cancel each other out. This results in a striped pattern called an interference pattern, which shows the wave behavior of light. But in other experiments, like the photoelectric effect, light behaves more like a particle. In this experiment, it was shown that if you shine a beam of light with enough energy on a metal, it could cause some of the electrons to be knocked off. This result didn't make sense if light behaved like a wave. Trying to explain this effect, Einstein concluded that light transfers energy in discrete packets, which we now know to be photons. In the photoelectric effect, this is represented in the equation E equals hf, where the energy given by the light is equal to Planck's constant times its frequency. So if light, which scientists believe to be a wave, can act like a particle, can particles also act like waves? In 1924, a scientist named Louis de Broglie stated that they can. In addition, he stated that their wavelength can be measured, and that the wavelength, known as the de Broglie wavelength, is equal to Planck's constant divided by the particle's momentum. How did de Broglie know this equation was true? Scientists had already known that the equation for the wavelength of light was lambda, for wavelength, is equal to Planck's constant divided by the momentum of the light. It's actually very similar to the equation for the de Broglie wavelength of particles. Now you may be wondering how light, which has no mass, can have momentum if momentum is mass times velocity. That's because P equals mv doesn't apply to things traveling at the speed of light. For light, we have to use the energy-momentum relation, which states that E squared is equal to m squared times c to the fourth power plus p squared times c squared. We know that E equals hf, so this side can be simplified as h squared times f squared. We know that the mass of light is 0, so the other side can be simplified as p squared times c squared. Taking the square root of both sides, we get that hf is equal to pc, which we can rewrite as h over p is equal to c over f. And the speed of light divided by its frequency is equal to its wavelength. So we know that the wavelength of light must also be equal to Planck's constant divided by its momentum. De Broglie stated that this same equation could also be used to calculate the de Broglie wavelength of particles. From 1923 to 1927, there was an experiment done called the Davison-Germer experiment, which tested whether particles could really exhibit wave behavior. Inside a vacuum chamber, Davison and Germer shot a beam of electrons at a nickel target. There was also a movable detector which could measure the amounts of electrons from different angles. The results showed that there were differing amounts of electrons detected at different angles, which meant that the electrons were interfering with each other, which is wave behavior. This experiment proved that de Broglie was right, and he received a Nobel Prize in 1929. If particles can act like waves, why don't we see wave behavior from everyday objects? Going back to the equation, we see that the de Broglie wavelength of a particle is equal to Planck's constant divided by the object's momentum. For normal everyday objects, momentum is just mass times velocity. Macroscopic objects have a relatively large mass, and in this case, that means that we're going to have a very small de Broglie wavelength. For example, the de Broglie wavelength of a 1500 kilogram car traveling at 30 meters per second is about 1.5 times 10 to the negative 38th meters. For reference, the diameter of a hydrogen atom is 1 times 10 to the negative 10th meters. So we don't often see de Broglie wavelengths in our everyday lives since they're so small, and the wave behavior of particles is much more apparent at microscopic levels. In today's video, we talked about the de Broglie wavelength and the wave-particle duality of objects. I hope you enjoyed this video. Please subscribe, and thanks for watching.